Good day, I'm Dr. T and welcome to my office. So today I would like to talk about atoms and really what those things are. But to do so, we want to jump back in time about 200 years. An individual by the name of John Dalton sorts out really our modern understanding of atoms. And what he's doing is he's looking at a series of pure substances. Now at this point, we're talking early 1800s. We know that you've got pure substances. These are not mixtures. These cannot be separated by physical means. Now, some of these pure substances you can still separate. You need to use chemical means. You have to do a chemical reaction, and you can get two or more constituents that form together to make your compound. And we call these things compounds. But there are other substances that you can't do that for. No matter what you try, it is what it is. And we call these elements. So Dalton's idea is that, hey, there's something fairly important with these elements. Because when you take a compound and split it apart, you tend to get things that are elements. Now, there's a couple other quirks with these elements that lead to the idea that maybe everything is made out of these small particles called atoms. When you do a chemical reaction, you'll look and there will always be a fixed ratio, especially for a lot of different compounds that are in the inorganic side. The organic ones get a good deal more complicated, and thankfully we studied the inorganic ones first. When looking at these, though, you have a fixed ratio. If I have table salt, I'm going to have a fixed ratio of 23 grams of sodium to every 35.5 grams of chlorine. Okay, why? If it's not that fixed ratio, then lo and behold, it's not table salt. Additionally, it tends to be that I can always somehow get a whole number ratio of these things. Things are going interesting, as if everything is made up of really small particles. And that's Dalton's idea. He lays out, depending on how you want to cut it, about 5 core functions of what he thinks an atom is. So the first is that everything is made up of small particles. These particles aren't divisible. They can't be changed. Now, of course, now we know that there are ways of changing atoms. Think nuclear chemistry or nuclear physics for that matter. But at that point in time, and anything that doesn't involve, say, a nuclear reactor or the like, this holds true. You have atoms of a substance, you cannot change those atoms. Atoms of the same element, the same unchangeable thing, are identical. Atoms of different elements are different. Compounds are going to be made by taking more than one type of atom and putting them together in a fixed whole number ratio. And chemical reactions are going to be shuffling of those atoms. These atoms aren't going to be destroyed, so they're just going to have to be rearranged. They're going to have to be moved over. And this really is our modern understanding of the atom. It really wasn't cemented in place until actually the 20th century, but it does lay the foundation for modern chemistry. John Dalton's work on the atom led to what we know as the billiard ball model. In this case, we think of atoms as small, hard spheres, kind of like the balls you used to play pool with, called billiards in some other places. Now, we know that these balls are made up of stuff, and atoms are made up of constituent parts. But this wasn't known in the early 19th century. It would take till the early 20th century to understand what was inside an atom. But simply knowing that you were dealing with small, presumably hard spheres that were rearranging was a profoundly useful thing to think about when dealing with chemistry. But let's take a gander inside these atoms. As the 20th century begins, we start getting a few clues as to what's going on with these. One of the first is the existence of the cathode ray. If you take an electric current and you split it apart so that you have two electrodes, a cathode, which is going to be the negative side, and a anode, which will be the positive side, and run a high voltage through, then you can get a beam of electrons going from the cathode to the anode. But of course, if you haven't discovered the electron yet, you just know you have a beam of charged particles, called a cathode ray. This is the core constituent of the old CRT TVs, things that are pretty much dinosaurs at this time. But this did give us a clue that there was something else going on. It took us a bit of time, but we realized that, hey, these electrons were small particles coming from atoms. And we went through a few different models. We had the thought of the plum pudding model, in which case the electrons were like raisins in plum pudding, or think bread pudding is a bit more common these days, floating around inside a positively charged atom. Then we did some rather interesting experiments. A guy by the name of Rutherford took some gold foil and shot alpha particles at them. Alpha particles are a helium nucleus. Of course, at this point, he didn't quite know this, but he knew that they were much larger than electrons and were positively charged. Most of them went through the gold foil, as was expected, but some of them bounced off. As described by Rutherford, this was as if shooting a cannonball at a tissue paper and it bounced. Something was odd. What we realized is that the positive charge and nearly the entire mass of the atom was located in a really tiny spot, much, much smaller than the already very small atom. The atom is going to be made up of electrons buzzing around, and I use the non-technical word buzzing for a reason that we'll get to later on. It turns out the electron behavior is, shall we say, complicated at best. But the electrons are buzzing around a central nucleus that has the positive charge that counteracts the negative charge of the electrons, as well as basically the entirety of the mass. Electrons do have mass, but they don't have much, and the amount is almost negligible. And now to the nucleus. The nucleus of atoms will consist of several subatomic particles, although they only come in two types, the proton and the neutron. The proton was discovered first, with the neutron coming several years later. The proton was more easily discovered because it has a positive charge. Magnitude-wise, it is equal to that of the electron, but of course opposite to that of the electron. This will govern really the chemistry of the atom. The electrons are where atoms interact with other atoms, and therefore what we think of as chemistry, and those are attracted to and strongly affected by the nucleus. The attraction to the nucleus? That's electrostatic, and frankly, it's the positive charge on the proton attracting the negative charge on the electron. For this reason, the number of protons within the nucleus, and therefore the magnitude of the charge on the nucleus, is absolutely critical. This is the feature that makes a specific atom a specific element. So if your atom has 6 protons, it is carbon. If it has any number other than 6, it's something else. And if it has 6, it's carbon. It's not something else. Now, the ratio of electrons to protons does impart some fairly relevant features to the atom. Generally speaking, when I say the word atom, I'm implying it's a 1-to-1 ratio. So the net charge of the atom is 0. So if I have a carbon atom, it would have 6 protons and 6 electrons. But electrons can come and go from an atom. And if they are not canceling each other out, the atom will have a net charge. Unfortunately, because of the way we defined charge back before we had discovered the atom at all, this makes it a little bit more interesting, because if you add electrons, because they are negatively charged, you will reduce the charge on the atom. It will become negative, and if you take electrons away, then it becomes more positive, which is a tad bit annoying. So for this, you can take the number of protons, subtract the number of electrons, and you'll get the charge on the atom. I should point out that we call atoms with a charge ions. If there is a surplus negative charge, we call it an anion. And if there is a surplus positive charge, we call it a cation. The last subatomic particle we need to talk about is the neutron. Neutrons don't have a charge. They generally don't affect the electrons buzzing around the atom, but they do have mass. Both the proton and the neutron have a mass approximately equal to 1 Dalton. 1 Dalton is 1.7 or so times 10 to the minus 24th grams. So we're not talking much, but we are still talking a good deal more than that of the electron. The neutrons present in the atom exert strong nuclear force on the protons. The protons do as well. And this keeps the nucleus from ripping itself apart. Remember, protons are positively charged, and while opposites attract, likes repel. So if you have more than 1 proton, which of course would be all elements other than hydrogen, then the nucleus is trying to rip itself apart from the electrostatic charge. The strong nuclear force is stronger than that and is supplemented by adding extra neutrons. Neutrons add strong nuclear force, but they don't add charge, so they're not trying to pull the thing apart. That said, once you get to a sufficiently large enough atom, there's no amount of neutrons that's going to keep it from ripping apart, and that leads into nuclear chemistry, which is for another video. Because the neutron doesn't have a charge and doesn't directly affect the electrons, two atoms of the same element could have a different number of neutrons, and that's quite common. These are known as an isotope. Isotopes will have the same chemical properties. There might be some minor differences because the neutrons do add mass, but they don't add charge. The mass can make the atom move a little bit slower or a little bit faster, and it will change chemistry just slightly, but typically it's not much. Now, the key part with the neutron is that both it and the proton have about the same mass in Daltons. We're going to be looking at atom's mass here in not too long, and that's going to be relatively important for us. So the sum of protons and neutrons is going to give us our atomic mass, which is something that's fairly useful for us. As I conclude this video on atoms, I'd like to recap of the three numerical values we usually assign to an atom. First is the atomic number. This is simply the number of protons. The second is the atomic mass, which is the number of protons and neutrons. Since both protons and neutrons have a mass approximately equal to 1 Dalton, the atomic mass is simply the number of the two added together in Daltons. Now, I will point out that the mass of protons and neutrons do change depending on how many of each you have, with atoms further away from iron typically having somewhat higher protons and neutrons than those that are closer to iron, or iron itself having the lightest weight protons and neutrons. This is something known as the mass defect and will be incredibly important in nuclear chemistry and is the origin of the mass in E equals mc squared, and thus the energy in E equals mc squared. The last one I want to bring up is charge. This is protons minus electrons, and this will govern quite a bit of the chemistry of ionic compounds because different charges, different ions. With that said, have a wonderful day.